Hello, I'm Liao. Welcome back to Evan of Code 2023. We are solving programming puzzles every day and we are on day 14. And let's take a look at what puzzle 14 awaits for us. So day 14, Parabolic Reflector Dish. We reached the place where all the mirrors were pointing. A massive parabolic reflector dish attached to the side of another large mountain. The dish is made up of many small mirrors, but while the mirrors themselves are roughly in the shape of a parabolic reflector dish, each individual mirror seems to be pointing in slightly the wrong direction. If the dish is meant to focus light, all it's doing right now is sending in a vague direction. The system must be what provides the energy for the lava. If you focus the reflector dish, maybe you can go where it's pointing and use the light to fix the lava production. Upon closer inspection, the individual mirrors each appear to be connected via an elaborate system of ropes and pulleys onto a large metal platform below the dish. The platform is covered in large rocks of various shapes. Depending on their position, the weight of the rocks deforms the platform, and the shape of the platform controls which ropes move and ultimately the focus of the dish. In short, if you move the rocks, you can focus the dish. The platform even has a control panel on the side that lets you tilt in one of four directions. Right, the rounded rocks, which is O, will roll when the platform is tilted, while the cube-shaped rocks, which is a hash, will stay in place. You note the positions of all the empty spaces, which is the dots, and the rocks. For example, this is the puzzle. Start by tilting the lever so all the rocks will slide north as far as they will go. Right, so all this will slide all the way up, and because the hash doesn't, like the square, a cube-shaped rocks does not move, then they will stuck here, right? You'll lodge here, and this will lodge here. And if you don't have, then you will keep falling. You'll keep rolling all the way to the top when it hits the hash, the cube rocks. You notice that the support beams along the north side of the platform are damaged. To ensure the platform doesn't collapse, you should calculate the total load on the north support beams. The amount of load caused by a single rounded rock is equal to the number of rolls from the rock to the south edge of the platform, including the roll the rock is on. Right, cube-shaped rocks doesn't contribute to the load. So the amount of load caused by each rock in each row is as follows. So I guess this gives us 1, 2, 3, 4, 5, 50. Right, 50 plus 9 is 18. And then we have 4 8s, so plus 4 times 8. And then we have 3 7 plus 3 times 7. And then we have 3 times 4. And then we have 1 of 3 plus 1 times 3. And then we get 136, which is this one. The total load is 136. So tilt the platform so that the rounded rocks all roll north. Afterward, what is the total load of the north support beams? Okay, so I guess this is the question, and let's take a look at how we can solve this. Let's try write our code. So here I have in my IDE, as you can see, we have the answers for every day since day 1 to up to now, day 14. And all this code, I have uploaded them onto GitHub. All you need to do is go to the link in the description box to find a link to the GitHub if you want to find all this code, right? So to start off, we create a input variable that will store this map of rocks. Okay, this is the default. This is the one. And next thing is we need to solve, right? We need to calculate what is the total load. So let's first define the variable called total load. and at the end of the code we need to print out the value of the total load. So now we have this input. Let's split it into rows and into an array that gives us a mapping of the map. So first is you're gonna create a variable called map is equals to input dot split by new line. Right. So what we need to do is we first thing is we want to know, we would like to know how many rows are there, how many columns are there, how many rows, especially because um, number of rows will determine, like if you have 10 rows, then the load on the first uh, row is actually needs to times 10, right? The load for each of the rocks here will have to times 10, right? So let's start with the total row equals input. So this will be basically map length, and total column is actually map 0 length, right? So map 0 is basically one line over here, and how many characters here will be how many columns we have. Okay, so there's so now we basically roughly know the map, number of rows, number of columns. Now we need to we need to figure out, calculate how we then figure out how to calculate the total load, right? So one way you can do is basically try to move all the zero, right, all the rocks up to the topmost position, right? Move it up as much as possible, right? Shift it up, and then we have to go through the entire map and try to shift up the rocks, and then we calculate for each of the, and then we iterate through the map again for each of the O position, right? We need to calculate how much load it carries and then add it up, right? So that will be one way that we can do. But actually, we don't really have to move the rocks up in order to calculate the load. We can figure out by as we are iterating through, we can actually whenever encounter a rock, we can actually sort of calculate what is the where this rock will eventually end up with, right? And then we, based on that, we calculate the load that it carries. How do we know where it will go up to? Well, we can iterate through column by column, and in each column we can see that if currently is if it's empty, uh, we can iterate through the column, and then whenever we run into a rock, then we know then if we know that previous on top of it there's no way to roll to, then this will be the final location. But then if it goes to somewhere with an empty space, then we know that this is potentially somewhere a rock can roll to, then we keep track of it, and whenever we encounter a rock, we know that this rock will eventually roll to this empty space, right? So that's where we will be that's where we will roll our rock to, right? So this is, we kind of know the target location of this rock eventually will roll to, and that's what how much load that this rock will eventually weighs, right? So which means that we will have two pointers, one pointing where the load is going to be, and one pointing where the one trying to find out where to go through and figure out where the rocks is, right? So let me try to draw it out and see whether it makes sense to you. So let me find a hold on, let me find a brush and let me try to draw something. Okay, so here I have my brush. It's cool. Okay, so here, for example, I have two pointers, one pointing here, and then one trying to find out, one trying to. Let me draw it this way then. I guess because of that, let me draw it this way. Okay. So I have pointer to tell me where I'm looking at, and also another pointer that basically tell me what uh where the rock will roll to, right? So at first this two is pointing the same thing, same location, then it means that this rock will eventually roll to the same place, right? So this, we know how much the load weighs, this rock weighs. And then since we already have a location for the rock, then the next thing is we are going to move our we need to move our arrow down right here, and find also the next place that you can roll to is the next location already. And this again is the same rock, so this rock will roll to the same place. So we move on, and then now we are here like this. So this is the new place where the rocks would roll to if we have another rock, but this is not a rock, right? So we're gonna move on and look for the next place, right? So our pointer for the finding the rock is move up, move down, and then we find here, and then we realize that this is a rock. Then this rock will definitely roll to this place, right? So roll to where this arrow is pointing. So basically, based on this, we know how much this rock weighs. So we can move on, like move forward, and also the location of the rocks that can roll to will also move forward, and then we just keep going like this. So not like this now. This is not a rock, so we move on, right? And then we move on to here, and then we found that this is another rock, so this rock will move to this location, right? So this basically the weight of this rock we know is basically this row, right? How much this row weighs. And we just keep going on. So the next rock that will roll to will have to go here, but then we keep going on like here, 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 and here we realize that we don't see any rocks. Then that's it. That's the end of the iteration, and then we go to look at the next column. And so by this we can keep calculating how much the load, the eventual load the rocks would carry without actually rolling or updating this map, right? And what happens if we encounter, for example, where we are here, okay, and then we come here, then basically we say that this rocks have to go here, right? So we point here now, and then we keep looking, right? This is not a rock, this is a hash. This is, so whenever we encounter a hash, then I guess next place that the rocks can roll to should be the next location right after the hash, right? Because the rock will not able to go through this cube rock, right? So if we find anything here, then we can roll here. But if not, we'll just keep finding, right? So this is the rough idea of solving, estimating where calculating where the instead of, this is how we're gonna solve this, right? Instead of actually modifying the map to roll the rocks over, we just go through one iteration, have a few pointers to let us know where to know where the rocks would roll to, but we don't have to modify the map. We just need to know where it would roll to, because all we care is the total load that it will carry, right? Which is based on where the final location it will be, right? But we don't have to show or print out the actual final location, final results. So a lot of times, solving problems like this, when we don't really have to know final results, and maybe it's not important, then we don't have to actually compute it out. Of course, it will be useful for debugging if you run into situations then you don't know why this is so, then probably you will have to print it out. But in our case, all we care is the total load, so we don't have to actually moving the circles. We don't have to modify this map, right? So back to our code, let's figure out how we can write this, right? So first thing is we're gonna go column by column, right? So I'll loop through column equals, we start with column 0, column less than total column and column plus plus, right? And then for each column, we're gonna have 2 pointers. One is pointing where the rocks would be, right? So I'm gonna say the a right. So the rocks, where the rocks would be, right, is basically I mean, let me I'll call it a variable called load, right? Because that's how much load it will be. And this value is actually equals to the total row, right? It will start with total row and then decrement, right? So it starts with 10 and then 9, 8, 7 will decrement by when we move down a position. And then we need a pointer to basically find where the rock positions are. So that we are going to call it row equals to 0, row less than total row, row plus plus. And as we move down the row, right, at the same time, we actually can also keep track what is the value of the load if we're going to update that the row is, and we can use it to update our load if we encounter something like a cube rock, right? So here I'm gonna have another variable called a row load equals to, it will start with the total row, but then it will also decrement, right? So this is basically the load for this current row. So the current row is 0, but the load is total row, right? And then as we move down, the row will increment, but the row load will decrement, right? As we move down, the row load will decrement. So as we go down each row, if okay, so now this is where we're gonna see whether we are running into a rock, a space, or a cube shaped rock, right? So switch between the map. So row, column, right? If it's this one, then we need to add the load up to total load, right? If it's this one, then we need to update the load value, and default or that we do nothing. If it's a dot, then we do nothing. Okay, and so here what we need to do is total load plus equals to the load value, and then load will decrease because we will move the load down to the next value, right? Shift it down, shift the pointer down. This we go to break, and for this one we need to update the local load value, right? So when we run into this, then the next place that we put is one value down, right? So the load for this one is basically, the load is gonna be equals to a row load minus 1. And if we run into dot, then we do nothing. And I guess that's it. That's the whole thing. Okay, so let's try to run our code. Node day 14 and get 136, which is exactly the same as the example. So let's go to get the actual puzzle input. Wow, this is a huge map. Let's copy this and let's paste this in. Let's run. Get a number. Copy this. Come back. Gonna paste it in. Hit submit. And yes, that's the right answer. Right, so we got 1 gold star and we are moving towards part 2. So on part 2, the parabolic reflector dish deforms, but not in a way that focuses the beam. To do that, you will need to move the rocks to the edge of the platform. Fortunately, a button on the side of the control panel labeled spin cycle attempts to do just that. Each cycle tilts the platform 4 times, that each rounded rock roll north, then west, then south, and then east. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. After 1 cycle, the platform will have finished rolling the rounded rocks in those 4 directions in that order. Here's what happens in the example above after each of the first few cycles. Right, so after the first cycle, which ended up like this. Okay, so I guess like it goes north, west, south, and then west. North is going up, west is going to the left, and then south is going down, and then east is going to the right. And after 4 turns, you will end up like this. So 1 cycle end up like this, and another cycle you end up having like this. 3rd cycle is like this, and this process should work if you leave it running long enough, but you're still worried about the north support beams. To make sure that they will survive for a while, you need to calculate the total load on the north support beams after this many number of cycles. In the above example, after this cycles, the total load on the north support beam is 64. Run the spin cycles for this amount of cycles. Actually, what is this? I have 1,000, a million, a billion. So 1 billion cycles. Run the spin cycle for 1 billion cycles, and afterward, what is the total load on the north support beams? Oh no, 1 billion cycles? Are you nuts? Okay, let's see how we can solve this, right? So let's close this. Let's copy the code into puzzle 2. And let's collapse this. Let's copy back the original input, right? This is the original input. Let's copy this. Let's come back. Let's paste this in. Alright, so this is the inputs, and so now we are gonna do the up, left, down, right, and that is 1 cycle, and we're gonna keep doing that cycle 1 billion times. And as you would have guessed, we probably it's not gonna do 1 billion cycles, because if you do 1 billion cycles, if you keep doing 1 billion cycles, it would so when you see a question like this, when it says go a billion cycles, I think it hints us something. It tells us not to try to simulate it 1 billion cycles, because 1 billion is too long to do so, right? 1 billion, if you search for, if you search for 1 billion seconds, that is a billion seconds, that is 31 years, right? Even if you can do as fast, 1 billion, if you just do it, it's how many years of time to simulate this, right? So it tells us something, right? The way it asks this question, it tells us something that you can't simulate 1 billion cycles. Okay, so which means that most likely than not, we will be it's either we settling down into some sort of the same pattern, or it runs into a cycle where basically after a certain uh, after certain configurations, when you do this again, it kind of go back to the same state over and over again, right? So it could be the cycle itself could be maybe like this. The next you do this cycle and the next cycle is the same, and next cycle is the same, next cycle is the same. Or it could be you do this and then maybe like the like cycle 2, cycle 3, and then cycle 4. It looks like cycle 2 again, and then cycle 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, right? Which means that maybe there is some intermediate states, intermediate cycles, but it repeats itself, right? So if you can figure that whether uh, but it's most likely either case, right? It's most likely it's like repeat itself where the loop itself is every cycles, or it takes a few cycles to come back to the same state, and then a few cycles come back to the same state, right? So this is more general than the cycle itself. The loop itself, it's just uh one cycle, right? And it will definitely go into this kind of loop because we know by asking this question to ask us, it's unlikely that we are going to simulate 1 billion cycles, right? So it definitely have some sort of loop. Okay, so I think our job is to figure out when does that loop happens, right? So we can simulate a few cycles, and then if we see that uh, a certain loop appears, then we can base on this loop and extrapolate to know that okay, how many times does it when we hit a billion times, how many what will be that state in within that loop, right? So so that is our approach to this problem. So let's go back to our code. Okay, so which means now, because previously we are kind of like um we just calculate the load without actually like making change of the input, right? We just assume that okay, this is um we just figure out what is the final position and then calculate the load, because we just need to tilt the we just need to tilt the map once. But now we need to tilt on both multiple directions, and then we need to record the state after one cycle. Then that gives us an idea of and we need to record that down so that we have a rough idea of what is the states after every cycle, so that we can check whether we are actually getting into some sort of loop, right? So which means that here we need to actually rolling the rocks. Okay, so I guess most part of this code will sort of like not whole, right? Um, so let's write a rough structure of the code, right? So the first thing is that maybe we don't even need the total load for now. Okay, so the rough structure is that this is the cycles. We need to go to a billion cycles, right? So let me separate it out with underscore so that you see it clearly. It is 1 billion. And so we start with I equals to 0. And while I less than cycles, right? It's gonna always be less than cycles. Then we are going to basically figure out the next cycle, right? So here I'm not gonna do this now. I think I'm gonna have it this way. So I will have a map equals to input, and then I'm going to say map equals to cycle the map, right? So I'm going to implement this function later on, but basically we're taking this current map and then we get a new map after the cycle. I think I need to also probably return two things, right? The map and the load, right? I think we can also get the load as well. Right, so we have the map and the load coming from the cycle, right? So map, we will go and do another cycle, right? And then the load give us the value of the current load, right? So uh, let me think. Actually, I don't need this one. I just need to know the map, right? Cycle the map, and then we get the next map, and we're gonna keep. And this map is basically a string, right? This basically we start with this string and then return another string, and I'm gonna keep track of which index this map refers to, right? So it lists give us an idea of if whether we come back to a loop, right? So an example is that I'm gonna create a map, create a map index is a map index, set the map with the current index, which is I. Right. I think I plus plus from here, I. Right. And of course, if map index has the map, basically, which means we have already run into a loop, then we want to figure out I think we need to figure out what would be the map value at cycles, right? And then of course we're gonna break out this loop. Probably gonna assign it to something, right? And then total load equals to calculate load based on the given map, right? And then this is what we're gonna print out. Okay. Okay. So here, let's see. So for example, say we have maybe have something is 1, because this, when we do the loop, we're gonna set, right? The first item is 1, second item is 2, 3, and then maybe 4, and then maybe 5, and then maybe we run back to say Z is at 6, right? So here we are, here is where we basically see that we already find the same index. We found an index which is the previous value is basically 3, right? So I guess first thing is the current index is I, which is 6, and const previous index is basically map index dot get map. This gives us something like a tree, right? And then we need to extrapolate to figure out what's the value what's the value when it is at 1 billion, right? So I guess first thing is that that 1 billion is to minus of three values, right? So 0, 1, 2, 3, 4, 5. So let's say we want to guess what is number 10, right? 10 minus 3 values give us 7. And for this cycle, we take every 3 elements repeats again. So we're gonna modulus by 3. This gives us 1, which means it is probably this, maybe 3 plus 1, 4, right? I guess. Let's see. So this should gives us a, right? Because after you get Z, you get B, you get Z again. Z is the same thing. You do the same cycle, you get B to A. So you get A, B, Z, and then A again, right? So which means for 10th one, we need to minus off 3 elements, right? And then so this one we get the cycles minus of the 3 elements. So 1, 2, 3, 3 elements, which this is basically the previous index. Okay. And then we're gonna see how many times do we go in a loop. So this basically one loop is 3 elements. This we can get this by 6 minus by 3. So this one we can get it through current index minus previous index. Okay. And then the remainder that we get, right? Basically we need to plus 1 from the previous index. Okay. And now basically we need to reverse find which one has the which map actually has the index at this thing. Okay. I guess we create another map called map reverse. Map index reverse. And then same thing, we just save the set map I to map. So basically this is the value we're gonna get out. So map is, I guess we can, from here we can know that the map at cycles is this value, is this one, right? And then we can break from here. We break this loop, and then since this is already set to the latest value, then this we can use this to calculate the load, and then we get the total load, and then we print out the total load that we have. Okay, so here we are left with 2 functions that we need to implement. One is the cycle function, and then one is the calculate load function. So for cycle, we are given a map, right? And we need to return a new map. So for this one, we will have a similar logic as we had previously. We're gonna break this down. Break map.split by new line. And actually for every line, we're gonna split it again. Right, so this gives us an array of matrix. I think I'm gonna call it map string. This is the map. This gives an array of a matrix of characters. And with this map, we are going to tilt north, tilt west, and then gonna tilt south, and then tilt east, right? So we're gonna for one cycle is north, west, south, east. Okay, and then at the end we get the map. Is basically map every row dot join and dot join with a new line. Okay, so for tilting north, for this one, what we need to do is we need to loop through every column, and then we're gonna assign. Actually, it will be quite similar to the code over here, right? I think. So we go through every column, and then for every row, so total column is equals to map dot 0 dot length, total row is map dot length. Okay, so here we have a initialize row, and then with the total number of column, number of row, we go through row. Let's see, I think we probably need to have an index somewhere to tell us where we need to swap it out, right? Okay, so the next equals to 0. We start with 0 and switch map row column. Case if it's that's either this one, let's copy this one, and a dot, right? If it's a dot, we do nothing. If it's a hash, then we know that the index to go to update to set the row next later on will be basically row plus 1 break. And then if we run to here, we're gonna update the map row column. Let's go to this one, and map index plus plus column is equals to this one, and break. All right, so we're gonna set this one to the rock, we're gonna roll it over, and then this we're gonna update this back to remove this to back to dot. Okay, so this is tilting north. Okay, I guess the logic is kind of similar for tilting south as well, except that we start with the total column minus 1. We're gonna go from the, hold on, no, every column is the same, right? Except that our row start with the last row instead. I'm going to decrement, and this one also total row minus 1. And then here, whenever here is -1, and index is minus minus. Okay, I think that basically we swap out. Previously, when we tilt north, is we start the row from 0 to the last row. Now is we from the last row back to the first row, right? And for tilting to the east is to the right side. I think one thing we'll swap out will be different is that we'll start with going through every row, right? Going row by row. This one we will just follow the total row. And then for every row, we need to look at column by column. So tilting is going to go from the last column to the first column, right? So this one will be the total column minus 1. We start with the last column, and we decrement to the first column, right? So everything, we start from right to left and then start to shift things over. And so if this is a cube shape, then this will be column minus 1, right? So it will be on the left side of it. And then for here, it'll be the same row, but then for index, it's index minus minus. Okay, I think that's roughly it. Then we're gonna copy this for tilting to the west as well, right? So for the west, we start from the column will start from 0, and while the column is less than total column, and then this is +1, and this is plus, and that's it. So let me just verify to see whether we actually our cycle function works correctly or not. So I'm gonna print out the map, right, after one cycle. Let me just set it this way first, and we're gonna go through 3 cycles. Okay, let's print out and see whether we get it. Sorry, puzzle 2, calculate load. Okay, ignore that, but let's take a look at our whether we have a printout correct, whether we flip it correctly, right? So first thing is, after one cycle we have this. Okay, after one cycle it let's see, compare, looks the same. Okay, so after 2 cycles it looks like this. After 2 cycles we have, okay, we have the same. Okay, after 3 cycles it looks like this. After 3 cycles it looks like this. Okay, so I guess our cycle function is working fine. It's correct. So so the next thing is we need to we keep this. Next thing is we're gonna figure out, we just keep cycle until we figure out what is the correct map based on the number of cycles, right? And then we're gonna have this implement this calculate load function to basically help us to calculate the load of the map, right? So for here, I am gonna say a, let me think. I'm gonna do the same thing, map.split by row. So this is the lines. And then to calculate, we're gonna copy back this logic. Maybe let me quickly copy over here. We have so total column, total row, right? So the total column is equals to lines dot length. Total row is equals to lines dot length. Okay, so the load, let me have a variable called total load equals to 0 first, and then we're gonna go through this whole loop. I'm gonna figure out, we're gonna increment, and then we're gonna return this total load, right? Which is the final calculated load. So for this one, how we're gonna do is we're gonna go through every column, and then we go through every row, and the load for that row is basically this value called the row load. Okay, and if this one is this value, then we need to calculate the load, right? So the load basically is equals to the row load, right? We're gonna increment by the row load. I guess that's it, right? Because I think the previous logic is we need to figure out where it will roll to, but now we already roll to all its correct places. We just need to calculate, just need to figure out what is the load for that current row, and then we add it in to our total load, and then finally return the total load. Right, so I think this logic, it should be okay. So let's try to run our code. I guess the hold on, something is not right. So let's take a look at what is the. So it seems like we didn't run into any of this, right? So let's take a look at what is the final map looks like. So this is how the final map looks like. Then I guess it should have some load, right? So let me try to see where went wrong over here. So we go from 0 to the column row less than total row, and the map for the row, oh, not map, this is lines, and the row at the column should be this one. Okay, so let's run again. We get 64, and the answer for this one is 64 as well. So it sounds like we're kind of getting the right answer now. So let us try to put in the actual puzzle input. Let me copy this, copy, and let's replace this to the actual puzzle input, and let's try to run our code, and we get a number. Let's copy it in and hit okay. Yay, that's the right answer. So we have solved day 14. We got 2 gold stars. We have yeah, it's such amazing experience. So I think the hint for this question is that we know that it is impossible to loop a billion times, then which means that there will be some sort of cycle or loop that will be repeating, and so we need to find out that pattern, right? Once we realize that, then I think it's more of like trying to actual simulating and try to find out where is the loop, and then use that to extrapolate to figure out where in the end where what is the value if we keep continuing this cycle, right? So that's it for today, and we shall see you in the next day. Bye bye.